research activities involves CFD, in particular high-speed aerodynamics and development of new algorithms. Since 4 years, he has been investigating the potential of quantum computing for CFD. That's very interesting. Before joining Glasgow in 2015, he worked as a lecturer at the University of Liverpool. His first and second degrees are from Technical University of Delft and University of Twente, both in Netherlands. With this brief bio of today's distinguished speaker to the FDP, I invite Professor to take over and deliver his lecture. Thank you, and we welcome you, Professor. We are excited to hear your talk for tonight.
Okay.
Thank you.
Okay. Well, thank you, Professor, for this introduction, and thanks for the invitation to speak at this event. So I hope you can all see the slides and you can hear me. Is that okay?
Perfectly, sir. Perfectly okay.
Okay, that's great. Okay, so I'll start then with a bit of a background to how I came to studying quantum computing potential for CFD. So following on from the short bio, I'll say a few more things. So I got my first degrees from Delft, where I really started looking into high-speed aerodynamics and
I request participants to kindly mute your mics, please. Thank you. I'm sorry, Professor. Please go on. Professor, your mic is muted.
Is it okay now?
Thank you, sir. We can hear you.
Okay, so good. So I started looking at high-speed aerodynamics about 20 years ago, and then from the start, I investigated CFD, but CFD, as in my research work, has always been about applying methods, but not just applying methods, but also developing methods. So from the early days, of course, we were involved in parallel computing. So this carried on, and since then I've worked at University of Twente, also in the Netherlands, on method development for incompressible flows. Then I had a stint at the University or the Caltech in California, and then I continued working on CFD methods mainly for multi-phase flows in Munich, and since 15 years or so I've been in the UK. So first at Liverpool, and since 2015 at Glasgow, where, as the introduction said, I work mainly on high-speed aerodynamics, but the range of applications is actually quite broad, but the main focal point actually is method development. So, and I'll mention more about this in the coming slides. So I'll just give a first outline of this presentation. So I looked at the theme of this workshop, and it was quite intriguing. So what I'll try to do, and hopefully it fits with what you've seen so far. So I'll give a bit of an introduction to quantum computing, in the hope that most of you will have at least some familiarity with it. So I hope I'm not repeating too many things you've already heard today. So then I'll say a few things about the CFD methods that in our CFD lab at the University of Glasgow we are working on. So in the lab we work mainly, or actually exclusively, with methods that we develop ourselves. So we have two main methods that I'll say a few more things about later. And then a key aspect of this presentation, and I think that's probably fits closest to the theme of this workshop, is where I see opportunities and key challenges for quantum computing in CFD. Because I think, and of course I'm just expressing my opinion here, there is a lot of very good work happening in quantum computing, and some of this is showing excellent progress. But of course, as always, when a new technology or a new method or a new approach becomes available, of course, there is always this potential danger that things get slightly overhyped. So I think that's why, for me, it's an interesting thing to investigate whether and how quantum computing has potential for CFD. But I think that the jury is still out on that question. So I think there is plenty of opportunity, but there is lots and lots of work still to be done. So what these things are, I'll mention in this presentation. And since I've been working on these investigations into the potential and opportunities for quantum computing in CFD for the last 4 years or so, I'll then move on to explaining what kind of work we've done so far at Glasgow. So I'm leading this activity in Glasgow, and I've worked with a couple of collaborators on this, and we've done mainly 2 different things. So first, we started by looking at using quantum computers as kind of an accelerator. So what we did is we looked at the compute intensive part of, in this case, an incompressible flow solver based on the vortex and cell approach, and we looked at what can we do with a quantum computer in terms of solving the time-consuming Poisson problem. So that was one of the first things we looked at, and of course all sorts of challenges arose there, and many questions remain, I think, to be answered. But clearly it showed to us that this was one way of going forward with that. But of course, as I'll detail in later slides, that approach of using quantum computing as an accelerator, of course, is in many ways a sensible and logical way of looking at it. But of course, there are issues with it in terms of having to move data from the classical domain. So if you have a quantum computer acting as a coprocessor, of course, this means that some of the algorithm is executed on a CPU or an FPGA or a GPU, which means that you have to translate data, of course, from the classical realm into the quantum world. And of course, that, of course, in itself creates lots of challenges. And some of these issues are really quite significant. So the second line of work I'll talk about today is a class of algorithms where we are trying to avoid the transfer or the conversion of data between the classical and the quantum domains. And of course, that in itself creates a whole range, of course, of other challenges. But of course, in many ways, it would then avoid some of the issues related to things like measurement, noise, and the collapse of the wave vector and the need for multiple realizations, etc., etc. So that work is very much ongoing. So I'll give a brief overview of that, and then at the end of this talk, of course, then I'll try to wrap up what my key findings are, and from those findings, of course, you will then see that, in my view, there is definitely scope for quantum computing in CFD, but to be perfectly fair, there is a whole range of challenges that remain, and some of these questions are quite fundamental and need very careful and much further work. So I'll complete the talk with that. So I'll start then with the background. So also, if I'll stop after I'll sort of split this presentation in about 2 or 3 different parts. So I think it's probably best if I open the floor for questions sort of halfway through or after a third of the talk. But I'll start with the background. So as I mentioned, in Glasgow we have a team of about 15. So it's myself and Professor Barakos leading that activity, and we have about 10 PhD students and a couple of postdocs on average working with us. And what we do is we develop CFD methods for a whole range of aerospace applications, and for the most practical applications, we have a solver called HMB3, and that's a very well established solver, and we've been working on this for about 20 years or so, on and off, with multiple academics and postdocs. So that's a very widely used solver and used for helicopter flows and wind turbines and high-speed vehicles, etc. Now, when I started as an academic in Liverpool about 10 years ago, HMB was already well established, but we were looking into developing a method of prototyping and testing novel algorithms and novel computational approaches. So in addition to that, to the HMP solver that we use and develop in-house, I also created a new research code, which is a framework that really allows us to plug and play and use the object orientation paradigm to build and construct a whole range of algorithms and create pilot solvers and prototype solvers. So it's less of a production solver; it's more of a fundamental research tool, and that's why we created it that way. And as you see on the slide here, even that research tool we apply to big problems. So, for example, in the past we have routinely used our solvers on thousands of cores, or even of the order of 10,000 cores for the biggest calculations. So clearly we are quite familiar with parallel computing and high performance computing. But of course, as you will all be very aware of course, that despite that, computers are of course never really fast enough. So you would always be looking for the next big step. And so what we do in Glasgow is a two-step kind of approach. So we try to have a Linux cluster available to us, and currently we are at over 1,000 cores, and that is so you see some pictures of older generations of the system. So that allows us to have an in-house Linux cluster with about 1,000 cores. And of course, for some of the biggest calculations we do, this is still not enough. So we also routinely apply for access to large-scale facilities, either in the UK, for example, at EPCC in Edinburgh, or the supercomputers that are available through European Union programs. So the kind of work we do, I'll just skip through this relatively quickly. So one of the things we have been looking into in recent years is high-speed aerodynamics for re-entry vehicles and space launchers and propulsion systems. So this slide shows you just an example of the Orion vehicle that NASA is developing or has developed and is now about to fly, hopefully next year. So this shows a relatively small example, actually. So this is the kind of job we do routinely now. But of course, it's still important to really look at the validation and the validity of the predictions. So here, for example, you see how our predictions for lift and drag compared to the CFD work of Murphy at NASA, and also, of course, whenever possible, we'll compare results to experimental data. Now, in the M5C solver, so the research framework I created, one of the driving design drivers was that we wanted to have something where we can really adjust the method that we use, but also the governing equations that are involved. So this slide shows an example where we solve the hypersonic flow around a wave rider, so the vehicle you see on the left. And the idea here is that we can change the solver in such a way that we can couple the Navier-Stokes equations in parts where the flow is close enough to thermodynamic equilibrium that this is physically correct, and in other places where rarefication or in this case strong thermal non-equilibrium occurs, actually we switch to model versions of the Boltzmann equation. So this is modeling hypersonic flows at a much more detailed level, so at the level of the Boltzmann equation. So rather than solving for conserved quantities like rho, u, v, and p, actually this Boltzmann equation solves for a particle distribution function. So it basically expresses in every part of the domain what the likelihood is of finding a molecule in that place with a given speed and state. Now that means that problem is computationally much more demanding. And therefore, what we did in that case is that the greenish regions around the leading edges here are the predefined domains where we select to use the Boltzmann equation. And in that domain, then we discretize this model Boltzmann equation using what we call a discrete velocity method. So the phase space is the space defining the possible velocity components as well as the internal degrees of freedom, is discretized then in discrete elements, and that means that even even for this relatively small extent of domain, we already have about 7 billion degrees of freedom. So clearly, this is the kind of supercomputing that we are doing at the moment, and this particular at one of the biggest supercomputers in Europe, in Munich, so the SuperMUG. So we run the solver at 8,000 cores to really evaluate it and develop this further. But despite the promise of these things, of course, it remains the case that we need more performance for some cases, of course. And that, of course, is what is ultimately driving our investigations into what kind of new hardware is coming online in the future, far future, but also the near future, and see how this can be used by us. So just as an example of another kind of hardware that we used in the past is the Blue Gene computer that was available at the Hartree Center in Warrington in the UK. And the Blue Gene is definitely not our favorite hardware because it's not really ideal for the kind of CFD that we do. But still, in the end, we managed to do some very large wind turbine simulations with 2 billion cells, as you see on the slide here. So that shows us that yes, we can use the current classical hardware, and even when we have to develop a parallel solver involving many hundreds or even thousands of cores, it is a real challenge. But this is what can be done, of course. So this is no longer really novel. It is still very much of a challenge, but it's sort of where we are in CFD. So of course, then the big question is what comes next. Of course, ever bigger numbers, of course, is one development, but of course, new hardware is also, of course, becoming available. So better use of GPUs, FPGAs, of course, is also something that we're looking into. Now, for this presentation, we use two elements of this of the M5C multiphysics code, so the research tool that I'm leading the development of in Glasgow. So this tool is built as a C++ object-oriented program. So what we have is we use template classes a lot, polymorphism, and what this allows us to do is really create generic classes that represent the discretization of problems on meshes, for example, or particle-based approaches. So that means we can do a lot of different things in a sort of a unified way that avoids having to reinvent the wheel and redo a lot of our work. So for the presentation that I'm giving you today, in red I highlighted the things that are really relevant to us at the moment. So when we started looking at quantum computing, of course we first looked at what is available and what problems will be most suited. And in this work so far, it is mainly a matter of the kinetic modeling that I'll mention, and an incompressible flow method based on the vortex in cell paradigm, where basically you've got like a hybrid between a particle-based approach, so the vortex particles carry the vorticity, but their convection or advection and their evolution also then is actually based on field variables that are actually defined on a regular mesh. So I'll mention this method in more detail later. So clearly, extending this to a quantum computer is by no means trivial. So when I mention here a quantum computing capability was added, the way to look at this is that what I did is I extended the C++ development environment to include a quantum computer simulator facility. So this means that for example, when you solve an incompressible flow using Poisson solvers, as they're commonly used, then effectively, instead of using the usual Fourier functions that you would write in a classical approach, this method then would allow you to say, okay, this Poisson problem now is actually not computed on a classical computer, but instead it is evaluated on, for example, a quantum coprocessor. So the M5C framework now includes a facility to really simulate the quantum algorithm part of a hybrid approach in that method. Now, of course, for the newer algorithms I'm looking at, which are more executed on the quantum hardware than on any kind of classical hardware, of course, that means that more and more of that work is actually done by the quantum simulator. Okay, so just to go back a step, and I'm sure, so the next few slides I'll just give some background, and hopefully from that it becomes clearer how we came about studying quantum computing for CFD. So as I mentioned, clearly CFD has always been pushing the available supercomputing hardware. So I think it's fair to say that whenever the hardware vendors sell a bigger supercomputer, that CFD or fluid mechanics or turbulence modeling or combustion modeling in particular, for example, are amongst the applications that are really running on those machines. So that's been the case for decades. So clearly that also means that no matter, for the time being at least, no matter how much faster these machines become, we will find suitable applications for them, and that will be the case for quite a few years to come. It also means that whenever new hardware comes online and quantum computing is in that sense fits in with the arrival of earlier developments like the use of GPUs or FPGAs in computational work. But that in itself is slightly problematic, because as hopefully will come clear, my view is that seeing quantum computing as just another kind of accelerator is in many ways a logical way of looking at it, but it's also slightly problematic. Anyway, so the hardware that is now available, of course, is extremely limited. So you will all have heard of the NISQ kind of generation of hardware. So that what this means is that the current generation of quantum hardware is involving a small number of qubits, and here I put 20 to 50. The number, of course, varies from place to place. So probably very soon, the 50 should be replaced by 100, for example. But in relative terms, this is still a really small number. And also these machines have limitations in terms of how these qubits are connected to one another and in their noise cancellation and capability as well. That's why they're called noisy intermediate scale quantum computers. So this is what we have in the foreseeable future. And for that reason, that's for now the kind of hardware that we're looking into. Of course, ultimately, you would hope that quantum computers become available with thousands or even tens of thousands of qubits. So a qubit, of course, in this case, is the quantum equivalent of a regular bit in a classical computer. So just to repeat, I'm sure you've seen this before. One way to look at a qubit is for a single qubit, we've got a phase space defined by a vector psi in this case, and this means that effectively this state is in a superposition between a 0 state and a 1 state, and until we measured this quantum state, which means that the wave vector collapses to either 0 or 1, we actually don't know what information is being held. So that's really the situation for a single qubit. If you extend this, then of course you get a much bigger state space that I'll discuss later. Now, of course, 20 to 50 qubits is not a lot. So the real question here is, what can we actually achieve with such a NISQ-style computer in the coming years? Now, when I first heard about quantum computing, I was still an undergraduate student, and because these algorithms came out so Shor's algorithm was introduced in 94, Grover's algorithm in 96 or 97. These were really very impressive steps, but they were solving problems that were quite far removed from the kind of things that CFD investigators are doing. So Shor's algorithm, of course, is factoring composite integers. So it's a very brilliant algorithm, and very impressive, but of course it's far removed from the kind of things that are happening within a CFD solver. So Grover's algorithm doesn't have exponential speed up for this unsorted list, but of course it still creates a significant speed up in terms of, in this case, a quadratic one. But again, this is not really directly something that made an impact in the field of computational physics or computational engineering or CFD in a more particular context. So based on that initial work, of course, and especially the Shor's algorithm, of course, made a massive impact because it really showed something that potentially shows an exponential speed up, which is the sort of the holy grail that all subsequent quantum algorithms are, of course, striving towards. Achieving other tasks with quantum computers actually proved to be quite a challenge. So, of course, towards the end of the 90s and in the early part of the new millennium, of course, there was a wider range of algorithms. So, of course, the quantum Fourier transform, so the QFT I'll mention later, was one of them. There were also early methods to solve linear systems. So the HHL algorithm introduced in 2008. These were all brilliant works and really showed that there was definitely something happening there. But still, of course, applying these methods into real computational engineering applications is something that is far from straightforward. And that's one of the things that led me to this question a number of years ago, in terms of there is clearly a lot of progress, but of course we need to be realistic as well in terms of when and how can these algorithms actually run on available quantum hardware, and in doing so present an actual improvement, which is definitely a research question that hasn't been answered yet. And my activities in Glasgow are only a part of trying to answer some of those questions. Now, as I mentioned before, the qubit is, for a single qubit, is basically a superposed state between a 0 and 1. Now, the idea is then that if you then extend the number of qubits in what we call a coherent register, for a single qubit we've got a superposition of 2 states, and then if you add qubits, you get a state space that effectively is in a superposition of 2 to the power nq states. So we see this exponential growth with the number of qubits, and of course that's really what is behind this potential of many quantum algorithms in terms of creating a computational advantage. Now I put in a bold font here measurement, and that's really an important thing, and we'll come back to this later. But what it really means is that if you use nq qubits, of course, then the coherent quantum register then will have a superposition of 2 to the power nq states defined by this Hilbert space quantum state vector, and the amplitudes in that vector basically then define the square of these amplitudes defines the likelihood that upon measurement this state is found. Now, what this means is that if you measure this quantum state, what it effectively does is it partially or completely collapses depending on the measurement that you do, and then of course it gives you a number. So in other words, if you would like to actually extract all of these 2 to the power nq complex numbers, of course you cannot do that, because the measurement will only give you very, very partial information. And that's something that we should really bear in mind when we look at sort of the potential for speed up and what we call quantum parallelism. So the quantum parallelism is of course related now to the superposition, where you say I've got a small number of qubits effectively representing a much bigger degrees of freedom through the superposition principle, and that of course is then behind a lot of the algorithms. But of course, as I mentioned, this measurement is then problematic. So the idea is effectively that if you would execute a quantum algorithm, that you would first initialize this quantum state, And that in itself is actually a very challenging aspect of quantum computing that I will say a few more things about later, but it's something that really remains, in many cases, a big research question as well. But assuming we've got this initial state that is in the state that we demand it to be, then what most quantum algorithms do, they apply a series of gate operations to that state vector in the quantum circuit model. And then, of course, the question is, what do I get out of this algorithm? So typically, you want something out of it in the classical realm, of course. So what you need to do is start performing measurement operations. So if we start from a state defined by nq qubits, of course, we have 2 to the power nq degrees of freedom in superposition, and therefore we have a state space psi defined here by 2 to the power nq amplitudes c, and these are complex numbers. Now, there is a whole range of measurements, of course, you can do, but one thing you can do is say, if we now measure one of those qubits, so one of those nq qubits we measure, that means that we have a partial collapse of the quantum state, and we now have a coherent state defined through nq minus 1 qubits, which means, of course, that and then the amplitudes now will be modified because the sum, of course, so the quantum state vector is still a normalized vector. So this means that the measurement will then give us an idea about the state of the qubit that we measure, and the remaining quantum state is now a modified quantum state that still is normalized. So the norm of that factor is still 1. And of course, then in theory, we can then repeat that process until we know one of those original one of the original n to the power nq amplitudes exactly. But of course, this means that if we want to know all of them, we would have to have, of course, a large number of repeats. So now I mentioned the Shor and Grover algorithm, and one of the reasons why they work so well is that they really minimize the number of measurement steps that are required. So they don't really involve this process of farming out a small part of an algorithm to a quantum coprocessor and mixing this with a classical algorithm that computes the rest of the work. So in other words, the Shor algorithm, of course, it actually needs a lot of qubits. So it is actually slightly problematic to do some really large integer factorization. But the work it does is actually nearly all done within the quantum algorithm itself. So the idea is that you really then do the measurement right at the end, and then of course you can minimize the number of measurements, and therefore also minimize the number of realization that is needed. So I'll mention the circuit model later on. So the idea, and I'm sure you've seen this, so the circuit model is one way of looking at quantum computing. So what this means is that if you draw a circuit where each of the horizontal lines represent a qubit, in line with the classical kind of circuit diagram, then you introduce gates that effectively then apply operations to that quantum state, and you can either have gates acting on a single qubit, for example, the Hadamard shown here with H, and you can also have gates acting on multiple qubits. And one example is in this case the controlled phase rotation. So the R gate shown here uses one qubit as a control qubit, and in this case, if that control qubit is in the state 1, it will then perform a phase rotation over an angle 2 pi divided by 2k to that state. So that's actually one of the building blocks of quantum computing. So in doing so, of course, you have to concern yourself with things like, well, in a physical implementation of this circuit on actual hardware, would these gates actually perform the intended operation exactly? So this is so there may even easily be gate errors. So if you really look at the performance of quantum algorithms, things like the effect of gate errors needs to be needs to be something that needs to be investigated. And the other thing, of course, means that I mentioned measurement, and measurement is basically an interaction of a quantum state with the environment. And of course, and this is one of the big challenges in developing quantum computers, keeping a quantum state coherent is one of the major challenges in devising quantum hardware. So this means that this quantum state will at some point interfere or interact with the environment. And in doing so, one way of looking at it is that effectively what may happen is that you get an unintentional interaction with the environment, leading to an unintended partial collapse of the state space. And of course, you actually modify the behavior of your algorithm very, very significantly. And at some point, if the decoherence is too much, of course, this quantum hardware can no longer be used. So the time a quantum computer can stay in this coherent state, of course, is one of the key things that people are trying to optimize now. One other thing before I move on to the work I've been working on is actually an important aspect of how would you actually represent data that you would normally store in a classical hardware. So if you program your CFD method, of course, normally you would use a language like C or C++, like what I use, and you introduce arrays and vectors and things like that. Now, in a quantum computer, there are two main ways of doing this. So the first thing is what we call encoding in a computational basis. So what you could do if you need to represent a complex variable or a real variable, what you can do is switch, for example, to a fixed point representation, and then use a binary form of a fixed point representation using multiple qubits then to represent that state on a quantum computer. And so you can do this for integers. So you need, so then the accuracy and the range, of course, of that integer then is defined, of course, by how many qubits you use in the binary representation to represent it. And you can do the same thing then for real and complex numbers using, for example, a fixed point representation. This, of course, means that you do need a significant number of qubits, and also for a lot of operators, then you can really then question whether there is still scope for a real benefit in terms of creating a quantum speedup. So quantum speedup, what this really means is that relative to a classical algorithm, you're realistically aiming for an exponential speedup in terms of the computational complexity, because looking at quantum hardware, even longer term, it's hard to imagine that quantum gate operations will be executed faster than the operations that take place in current chips, in current processors. So this means that for a quantum algorithm to really outperform a classical algorithm, then realistically you're aiming for showing in complexity analysis an exponential speedup. Or at least a very good sort of polynomial speedup, because otherwise it's very unlikely that this ever will give you a real benefit. Now, the alternative approach to encoding variables in terms of fixed point representations is actually the one that is used in most algorithms that are involved in numerical simulations. So we've got the idea that if we go back to the slide here, so we define the quantum state psi through a series of complex amplitudes. In this case, the number of amplitudes equals 2 to the power nq, and nq is the number of qubits. So one way to do that would be to say, okay, I'm taking data that I would normally store in a vector, and instead of storing doubles and floats in a vector, I use those numbers and map them onto the amplitudes of a quantum state. So this is what we call the amplitude-based encoding of quantum information. Then now that sounds easier than it is. So one major issue is then the the method to initiate this quantum state, which is far from trivial, and in many cases is very problematic. And the other thing, of course, is that since quantum computing, of course, and quantum mechanics in general involves reversible operations and normalized state vectors, of course, we still need to be careful in terms of creating a normalized state vector onto which we only apply unitary transformations. Now, in the work I'm showing you today, we use the second approach, so the encoding in terms of amplitudes. So now, as an example of the quantum circuit model that I mentioned, and I'm sure you've seen this in previous presentations or in textbooks, you can look at the well-known quantum Fourier transform. So in this case, it's a 6-qubit version. So you see 6 horizontal lines denoting 6 qubits with the input on the left and the output on the right. And what we do is we have a series of Hadamard gates and a series of controlled phase rotations, where the number behind the 6 then determines the power. So we have an angle 2 pi divided by 2 to the power k, where k then is the number that you see behind the capital R's here. So you see that the more qubits we have, of course, then the smaller the smallest of the rotation angles will be. And this is actually another practical issue that actually arises when you implement this method, this quantum Fourier transform, onto real hardware. But another thing that you may have spotted here, and this is actually well known, is that if you apply the QFT this way, the output will actually have the quantum state with the bits in a bit reversed order. So this is actually in line with the classical FFT, where of course there is also a bit reversal operation taking place. So if you want to really use the QFT as the quantum equivalent of a FFT, of course, you have to be aware that if you just use the circuit I show here, the output will be in bit reversed ordering. But of course, in the algorithm that I'll show you later, actually we just account for this fact, and there is no need to really then rearrange the data before we actually use it. So that saves a bit of work and it saves a number of qubit swaps. Okay, so based on that, hopefully then you can see that just by virtue of having this state space growing exponentially with the number of qubits, you could sort of imagine that this is very attractive, because you can say, well, if I have a small number of qubits, in reality I represent data with a lot of degrees of freedom, so 2 to the power nq in this case, for nq qubits, that I wouldn't have on classical hardware. So that's mainly then the parallelism aspect of the quantum mechanics. Now the other quantum mechanics phenomenon that you can use is entanglement, which is actually less important in most algorithms I'm aware of that actually are used in numerical simulations. But of course there are examples where entanglement and also things like quantum teleportation are crucial aspects of the algorithm. But for CFD, the main thing, in my opinion, and what I've seen so far in the literature, is it's effectively the main benefit has its roots in the quantum parallelism that has itself then its roots in this exponential growth in the state space with the number of qubits. Now, in this work, we'll use the circuit model. So the circuits will definitely be far more complex than the 6-qubit QFT I showed in the previous slide. But the idea is the same in a way, that we have a horizontal line that represents the qubit, and then a series of single and multi-qubit gates then transform them. But one of the major limitations is that, so the QFT involved only 2 types of gates. So we've got Hadamard and controlled phase rotations. Most actual quantum hardware, of course, has a very limited range of gates available to it. So one of the things, of course, that is important, that as long as you can define a universal set, of course, then even if you define your work in the quantum circuit model through gates that are not actually native on the hardware, as long as this can be mapped onto this native set using an efficient compiler, of course, then you're okay. But because of the quantum mechanics, physics behind it, of course, all of these operations that you apply to the quantum circuit model, apart from the measurement I mentioned earlier, should be reversible and unitary. And that's actually a major issue, of course, in devising useful algorithms that relate to modeling flows or even things or any kind of computational engineering. Actually, this is a similar kind of challenge. Now, if you then use this amplitude-based encoding, so the idea is actually quite easy to sketch. So the one way to look at it is to say, if I would discretize a function f on a regular mesh with n points, so I've got n discretized values f underscore j in this case, what you can do is then define a quantum state vector where the n, so the capital N amplitudes, so capital N, of course, is the number of points in your mesh related to qubits through 2 to the power nq equals then n. So you can then, in theory, then, if the amplitudes are normalized, you can then just introduce those discretized values into C, and then of course you need, as I said, you need to worry about the fact that the state vector needs to be a normal vector. So you may have to introduce a subsequent renormalization. Now, as I said, this seems a lot easier than it really is, because initializing a quantum state in an arbitrary state like this, in a potentially arbitrary state, of course, is very problematic. So the initialization aspect of the quantum state is one of the major challenges in applying quantum computing to CFD. And as far as I see it, this issue hasn't been solved by a long stretch. So this is a major challenge. Now, the first thing I'll mention then, of course, is that even when you manage to define this quantum state, what we should really bear in mind is that the information is there, but it's only there encoded in the quantum state. So we've got this we assume now we've got this NQ qubit coherent quantum register, and that quantum state holds then this information. So as I mentioned before, if you then want to know what this information is, and you want to bring it back to the classical realm, of course you've got a big problem, because you would then have to start measuring it, and then the state vector collapses, etc., etc. So you would need to have multiple realizations of it to really get all the information. So one thing you can really see here is that as long as the quantum algorithm uses this kind of state vector and we avoid the need for measurements, of course we are okay, because in the quantum state, that number of degrees of freedom is fully defined. So one thing you can definitely see is that in algorithm design, you would like to keep this quantum state coherent as long as possible. So you would delay as much as you can the need for performing measurements to extract classical information. Now, if you really want to have the full number of degrees of freedom from the example I showed you, so n, capital N is 2 to the power nq, you would basically need of the order of n realizations of this state if you really want to measure and perform statistics and estimate what these amplitudes are. And that's a bit of a upsetting conclusion. So that shows that if you really think in terms of CFD and you would use this quantum parallelism to represent your flow field, so velocity components, pressure, density, and whatever else you may need, then one big issue is that if you really need at the end of the simulation all of that information, so you want these velocity components in every single mesh point, of course that means that there is no way you can get this by having just a single realization. So you will need a very large number of realizations to get meaningful estimates of then what the output is. So that's in a way what we call the output problem. So we've got an initialization challenge, and even if the quantum algorithm does exactly what you want it to do on that quantum state, and it does all the computational work exactly as you want, and that by no means is trivial, of course, then still, even at the end of this CFD simulation, of course, you would then be forced to sort of say, okay, if I really need all this information, I would have to repeat or simultaneously run multiple realizations of this algorithm to actually get what I want. And that's actually very important to keep that in mind. And the answer to this challenge or the solution to it hasn't been found yet. And so quantum mechanics, I don't think allows it. So we just need to think probably in terms of a different way of looking at a CFD algorithm in terms of how we define the output. So clearly extracting classical data is a problem. So if we would use quantum computing to represent, for example, the most compute-intensive parts of a CFD method, and effectively then use the quantum hardware as a coprocessor, of course, then you would typically every time step or every iteration in your CFD simulation be doing this transfer between the classical and the quantum realms, which is really problematic, because then this cost of reinitialization of the quantum state is significant, but also, of course, as I mentioned, multiple realizations are needed to get meaningful measurement results, which means that ideally you would minimize the number of occurrences of those steps. So by devising a CFD algorithm in which part of the algorithm runs on a classical computer and another part of the algorithm on a quantum computer, of course, then in a way it's unavoidable that repeatedly you're doing this transfer or this conversion between the classical and quantum worlds. And that's really problematic. As mentioned before, the initialization of a quantum state is really problematic. So in general, it takes order n work for n degrees of freedom, but there are definitely, and very fortunately for us, of course, there are exceptions to that order n estimate. So if the order n would be generally true, then for all quantum states, then we would, I think, be really struggling to get any useful work done on a quantum computer for CFD. But there are states that have been proven to be more efficiently initializable. So you can initialize them without the exponential cost. So that's a really important thing to bear in mind. Now, as I said, this idea of doing a hybrid algorithm is really a sensible one, because it sort of fits in with what we're in terms of using co-processors and accelerators like GPUs or FPGAs. So in many ways, it's a very logical way of going about developing quantum-based algorithms for CFD. But of course, there is an issue. So in this sketch I took from work by by Heiner, of course, there's a practical side to this as well. So apart from the fundamental issue with reinitializing and the cost involved in this and the need for multiple realizations, of course, if you would imagine that for the time being, of course, most quantum hardware would actually be in a cryogenic environment. So in other words, you would have a cryostat holding then this quantum coprocessor, and of course then this thing would have to communicate then with the rest of your hardware, which is for example then a standard kind of processor-based workstation. So clearly, if you look at this sketch and you think, well, how would it actually work? So there are ways of, so this information would have to be exchanged through pulses, and ultrasound has been looked at, etc., etc. And also you have to basically have one part of the hardware at room temperature where you can work comfortably, and of course then part of this hardware is actually stored in a cryostat. So even from a practical point of view, you can see that coupling those different kinds of hardware is far from trivial. Now, this slide, so the last challenge I mentioned, and this is something that is not my finding in that sense, it's something that is relatively well known, that representing nonlinear problems is actually quite problematic. So if you think back to what I mentioned about the amplitude-based encoding of the information in the state vector, so that means that if we use, for example, then this amplitude-based encoding to store velocity vector components in your different grid points as different amplitudes in the quantum state vector. Now, in a typical Navier-Stokes solver, of course, you need things like u squared, v squared, u times v, u times w, etc., for every grid point. So the nonlinear product terms, effectively. So just thinking about it from a very simple, well, it's not simple, but from a very fundamental level, what you would normally do in any kind of classical implementation, of course, you would just usually introduce like a temporary float or a temporary double and create then this product of whatever velocity component that you're interested in. Now, the no cloning theorem in quantum mechanics does not allow you to sort of make a temporary copy and then use it to multiply against something. So it's actually not straightforward, or actually it's extremely difficult to see how nonlinear product terms can be computed in the context of this amplitude-based encoding. And that's one of the major issues. So you see that there's in the whole overall quantum computing literature for ordinary differential equations and partial differential equations, there is a lot of progress and very, very impressive work and great advances in the last 10 years for linear systems. So linear ordinary differential equations, linear partial differential equations have all been tackled with quite an impressive range of quantum algorithms that have definitely got problems. But looking at the work dealing with nonlinear equations, you will see that there is a much smaller number of works, and most of the time these algorithms come with significant issues. So, for example, they wouldn't, from a complexity analysis, for example, they wouldn't actually show any kind of quantum benefit. Now, one way you could go around this problem is say, well, if I use this classical quantum hybrid approach, I could sort of say, can I just give the classical computer then the task of performing those nonlinear terms and then feed it back into the quantum state? Of course, that would be an option. So that's definitely something you can do, and people have tried it and it works. But of course, fundamentally, of course, you're still limited then by the fact that, as I mentioned before, this coupling of a quantum part of an algorithm to a classical part of an algorithm, of course, has its own challenges. So that's really important. And so just to summarize, and you may find this summary disappointing or inspiring or challenging or motivating, and to me actually it's all of the above, because I can see that there are a number of serious and quite fundamental problems when you're trying to use quantum computers to do numerical simulations in engineering. So in this case, CFD. Definitely there has been progress, and that's really good. And there is definitely a significant number of unanswered questions. And in my work, I'm trying to answer, or partially, or at least I'm aiming to answer some of those key questions. So the things about the measurement issue and the transfer between the classical and quantum realms, and also the nonlinearity. So, but these are still very early days, and I find it a challenging area. I find it really exciting, but clearly lots of work needs doing. So I think as a first sort of conclusion of this first part of the presentation, my view is that quantum computing has potential for CFD, but we're not there yet by any by any means. And I think we also should be careful not to overstate or overhype the potential, because there are some really fundamental things that need to be investigated first. So that's the first part of this presentation. So maybe it's a good idea now to sort of open the floor for questions, to see, because now in the rest of the presentation, I just want to then go into more detail about what I've been working on in the last year at Glasgow. So if there are any urgent questions now, maybe it's a good time to sort of answer those first before I go on to my work. Okay, I don't hear any questions, so okay, then if you're all right with that, I'll continue then with the rest of the presentation. Of course, if there is an urgent question, maybe it's best not to wait until the end and then just let me know while I'm presenting. Okay, let's then carry on. So, as I said, the most obvious or logical approach to deriving quantum algorithms for CFD would be in line with the idea of finding compute intense. So you look for, in your CFD algorithm, of course, first, what parts of the algorithm actually take the most of the CPU time. So for example, an incompressible flow solver, you will often find, for example, that the pressure Poisson problem is the most time-consuming part of the simulation. So so that would be an obvious starting point to say I profile my current quantum algorithm, and I look for which parts of the algorithm are consuming most of the CPU time, and for those parts I'm trying to devise then quantum algorithms with a better computational complexity. So that's the approach we took in our first work, and this was to do with incompressible flows through a method for the incompressible Navier-Stokes equation based on the vortex and cell paradigm. So the main building block of that work was the QFT, the quantum Fourier transform, and how we solved then the Poisson equation. Now, hopefully by now you will have guessed that and understood that by taking that hybrid approach, clearly there is a range of issues in terms of exchanging data. So as a second line of investigation, I started to work on what I call sort of more sort of full quantum algorithms. So full quantum on this slide basically means that we would like to go away as much as we can from this hybrid approach and perform more and more of the CFD algorithm actually in terms of the quantum state vector. But that of course means that things like representing nonlinearity are major issues, and by no means have these issues been solved. So just have a quick look at the QFT. I think probably you will have seen this before, but the idea for the QFT is really that it's the quant. So if you encode a vector in terms of the amplitudes, the complex amplitudes of this quantum state vector psi, of course, then the QFT effectively then changes these amplitudes into effectively the Fourier components that you would normally get out of the discrete Fourier transform. So that's the circuit is actually quite interesting. So looking at the circuit, then what you see is that the number of degrees of freedom, of course, in the classical sense, so n scales as 2 to the power nq. So we've got an exponential increase in the classical degrees of freedom with nq, the number of qubits, and the circuit, as you see here, involves a number of Hadamard operators that scales as the number of qubits, but those operators don't actually take most of the time. So the main complexity of the quantum Fourier transform is a quadratic scaling of the number of rotation gates in terms of the number of qubits. But that still means, of course, that compared to the complexity of the normal fast Fourier transform, which is n log n, we actually get a very meaningful speed up, exponential in this case. So that's very important. Now, one thing, of course, you can do lots of things with the Fourier transform. So lots of algorithms in computational physics and computational engineering, of course, use the fast Fourier transform. So from that point of view, you can also expect that for a lot of computational engineering applications of quantum algorithms, you would expect that the QFT would play its role as well. Now, one other thing I just want to mention is that if you look at the circuit for the QFT, you see that the control is done through the solid dots. So on the left of the circuit, you see that the zero qubit acts as the control to the next sort of 5 controlled rotations, and you see that the further the target qubit, in this case, for example, target qubit 5 is furthest away from qubit 0. You see that the integer behind r increases. So the 6 in that case means k in this context. So in other words, the further the target qubit is away in terms of ordering in the qubit register, you see that the rotation angle actually decreases. So that's actually quite problematic, because if you implement these rotation gates on real quantum hardware, reliably performing a very small rotation is a big problem. So one of the things people have looked at is instead of using the quantum Fourier transform, use what we call the approximate quantum Fourier transform, where we use what we call bandwidth limiting. So what you do is you say, for example, that in this slide, all the rotation gates are where the integer is above 4 or 5, for example, then trim them out. So that basically then limits the bandwidth, and it also then limits the smallest rotation angle that occurs. So that's really what band limiting QFTs, or in that case, creating an approximate FFT means. Now I'll just show you. I'll get to what this actually means for our Navier-Stokes solver, but just to show this, if you look at example algorithms that encode in the computational basis, and quantum arithmetic is an example, in the literature you can find full adders for integers based on the Fourier transform, the quantum Fourier transform. So one of the first things we did before we started actually developing the Navier-Stokes solver was to sort of investigate and study what the impact is of minimizing the number of rotation gates. In other words, this band limiting, because we want to, first of all, remove the complexity of the algorithm, reduce the complexity of the algorithm, but also then make it more realistic when, at some point, hopefully in the future, these algorithms would be implemented in real hardware. Now, for the integer addition, we did a systematic study, but I'll just show you some of the effects. So if you take this Fourier-based adder, so we've got the first block that computes the quantum Fourier transform. Then we've got a middle block in this slide that shows what we call the phase addition part of this algorithm, and then we do the inverse QFT. So you could involve the QFT with the bit reversal, but it's easier, of course, than to rewrite it and remove this reversal straight away, and you get the same results actually. Now, if you use band limiting, you get the following result, and there is a lot of information in this slide, but the way to look at this is as follows. Here we add 2 5-bit integers, and the result is encoded in the computational basis. So if we use the exact QFT, then the amplitude of the solution state squared should be 1. So in other words, you would expect upon measuring to find the correct answer. So you see that if you then limit this Q of t and the phase error addition stage, you see that the more you limit it, so the lower the k limit is, the more rotation gates you eliminate. You see that depending on the integer a and b, so the inputs are a and b, you see that you can look at what the likelihood is of actually measuring the correct answer. Now, from all that information on the slide, what you can see is that, of course, the higher k is, the fewer gates that are removed. So the approximate Q of t is closer to the full Q of t, and then of course the errors are correspondingly smaller. But what it also shows is that you can really quantify then the errors here, or the likelihood that you measure an incorrect answer. So for this kind of algorithm where you use this computational basis representation, you can do quite a thorough and analysis with firm conclusions about what the impact of this approximation of the Q of t is. So that was really useful thing to show us. But of course, the question now is if we would do the same thing to a solver in which the information is actually encoded through the amplitude. So this is what we'll show next. Of course, then this needs to be looked at in detail as well. But definitely, this previous analysis was useful in just getting a feel for what kind of errors are introduced when you start approximating the Q of t instead of computing the exact circuit. Now, just because in the interest of time, I'll just mention a few things here. So what we do in this first quantum algorithm is we solve, or we're attempting to solve, the Navier-Stokes equations in their incompressible form using a vortex-based vorticity-based formulation. So instead of using the velocity field directly, we actually introduce a formulation based on vorticity. So the curl of the velocity as shown on the slide here. And what we then do is we introduce particles that contain or carry vorticity. So the particles then are given then a finite stencil. So what this means is, so this means that in every point of the flow field where we have vorticity, you can then define a vortex particle, and then with the vorticity then carried in that particle using this function shown here through the contours here, you can then actually transfer the vorticity held in the vortex particles onto the underlying regular mesh. So that means then that in contrast to some vortex particle methods that actually solve the Biot-Savart problem, what the vortex in cell method does is it transfers the vorticity to the regular mesh, and then by solving a Poisson problem, we work out then the velocity again for this modified flow field. So instead of doing the Biot-Savart problem, we actually do this coupling between particle-based and grid-based. Now, in the grid-based method, of course, we've got our problems here. So what we have here is a range of Poisson problems that need to be solved, and the way we go about it is as follows. So in this case, once the vorticity has moved within a time step, the vorticity is taken from the particles and moved towards the grid, and then the potential function A, so shown here, A, is a vector function. So in 3D, you've got a function A with 3 components, of course, in every cell of the grid, and then the vorticity vector adds as a source term to that Poisson problem. So we solve for this vector potential A, and then we can actually work out what the velocity is in our vortex particles. So in other words, similar to what you see in fully grid-based incompressible Navier-Stokes solvers, you will see that most of the work actually that this method does is solving Poisson problems, and that's quite common in many incompressible flow Navier-Stokes solvers. So that's really the background. So the idea is then that we say, okay, we solve then these Poisson problems using a Fourier-based solver. And first we looked at just the exact solution. So we looked here in this case at the collision of two vortex rings and just looked at validating then this vortex in cell method. So you see that two vortex rings are approaching, they stretch and do very interesting things. They don't merge because the vorticity is opposite sign in this case. So they don't merge, but they sort of push each other away and stretch. Now, as I said, the crucial thing here is that so now the assumption is made in this hybrid method that the quantum part of the hybrid algorithm solves the Poisson problem using a QFT-based Poisson solver. And of course, one of the first things we then needed to look at is once we then transfer the solution from that quantum algorithm to the rest of the algorithm, so the algorithm that is executed on the classical processor, of course, we have to account for the fact that in a real realization of this hybrid algorithm, their solution would involve noise. So one of the things we did in the computers and fluids paper we wrote a couple of years ago was really do a systematic study where we looked at what level of noise coming from the measurement of the quantum solution of that Poisson problem can then this approach based on vortex in cell still cope with. So that was what we found. So we found limits to the level of noise that is acceptable. So that's one aspect of linking then this quantum-based Poisson solver to the rest of the Navier-Stokes solver. And the other aspect we looked at is this band limiting of the QFT. So as I mentioned before, if this for a 256 cube domain, of course, effectively the Poisson solver in the quantum context will perform the QFT on 8 qubits. And of course, that means that some of the rotation angles are really small. So the smallest angle is 2 pi divided by 2 to the power 8. So it's a really tiny rotation that some of those rotation gates in the QFT are doing. So one other aspect of devising such a hybrid algorithm really is to say, what can we do in terms of making this hybrid algorithm cope with the impact of bandwidth limiting the QFT in the Poisson solver, that is the quantum part of this algorithm. So we looked at a similar test case, just out of interest. We looked at a different state, which is now the leapfrogging of two vortex rings. So this is again the exact solution. So then the next step is actually then where we say, okay, compared to the exact solution, where we don't band limit it, we now are going to limit. So the exact solutions were on the previous slides. We're now going to limit the QFT in the quantum algorithm, and you see that, of course, the smaller k limit is, of course, the more rotation gates are ignored, and you get, of course, errors and noise being introduced. But again, what this allows us to do is to investigate and assess, and also even quantify what level of approximation is acceptable to this particular Navier-Stokes solver. So that's really this initial work we did, and of course, in terms of further work, this needs being looked at further. So this is a very particular type of Navier-Stokes solver. So that what we call the vortex in cell method, of course. But similar things, of course, in terms of Poisson-based incompressible Navier-Stokes solvers, of course, you would need to be looked at in a similar way, where you would have to look at what is the impact of the noisy solution of that Poisson problem on onto the rest of the solution process, and also this impact of bandwidth limiting the QFT. So that's really the conclusion. So of course, if you as you see from this slide, if you limit the Poisson, if you limit the QFT in the Poisson solver too much, of course, you create noise that just spirals out of control, and your solution process doesn't work any longer. So clearly, some bandwidth limiting is acceptable, but clearly you can see that there is definitely a limit to what can be achieved. Okay, now that was all the first steps of the work, and this is still ongoing work, and I can really see there being more scope to develop this much further. So I hope to get one or more PhD students to work on this further in Glasgow, just because there are definitely a number of unanswered questions there. Now, to avoid this issue of measurement or not avoiding it, to minimize the effect of this need to reinitialize quantum state vectors during the course of a simulation involving hybrid classical quantum hardware. Of course, one idea would be to perform all of the algorithm, or at least more of the algorithm, actually in terms of the quantum state vector. So that's really what is sort of the more recent work I've been looking into, and there has been some progress, but clearly there is a whole range of challenges there as well. So what we did is we said, okay, we know that we can solve the Poisson problem, of course, using the QFT or the HLL algorithm, of course, but this coprocessor idea, of course, is as I mentioned a few times now, is of course fundamentally limited to some degree by the fact that the measurement and the reinitialization costs are significant. So avoiding this coupling approach, this hybrid classical, is probably overly ambitious. So I don't think it can be avoided completely, of course, because in any case, at the end, of course, we will need to extract classical data. But minimizing the amount of transfers between the classical and quantum domain, of course, is useful. So one way to look at it is at flows is actually not necessarily then through the Navier-Stokes equation. So what you will see in this second application is actually a modeling of the flow, not at the level of Navier-Stokes, but at the kinetic level. So at the start of this presentation, I mentioned the kinetic modeling, so the Boltzmann equation, where we effectively solve for a particle distribution function. And this is also, for example, used in the lattice Boltzmann method, but of course that's different from the discrete velocity method here, that is really devised in particular for non-equilibrium flows. But here it is similar. So rather than solving for rho, u, and v, you solve for a distribution function. And the first thing we looked at is that in the Boltzmann equation, the left-hand side of the equation, so before the equal sign, is actually a convection equation. So the first thing we looked at is solving convection equations on a quantum computer. And one way to do this, and there are multiple ways of doing it. So one way to do this is actually based on work I saw from a research group in Canada, where they looked at quantum algorithms to solve the Dirac equation. So what you can do is if you consider a one-dimensional convection equation on a uniform mesh, then you can always, of course, then say, while this solution is convected, you can use what we call the CFL is 1 condition. So the Courant-Friedrich-Levy condition is 1, which means that we choose the time step such that the solution jumps from one grid point to the next within one time step. So on a uniform mesh, of course, you can do that for the linear convection equation, where the convection speed is the same throughout the domain. So that allows us this kind of streaming operation. So what you do in a way is you say from one time step to the next, you can then either move the solution towards the left by one mesh width, or you move it to the right by one mesh width. And what is interesting is that if you look at an example of a 64 cell mesh, so you need 6 qubits. The circuits I'm illustrating here would actually then perform such a streaming step. So the X in this case is a NOT, and so we have controlled NOT operations where the full circle denotes conditional on 1 and open symbols on conditional on 0. So by devising such a relatively simple quantum circuit, you're actually performing a streaming operation where the solution encoded in amplitudes moves from one cell to a neighboring cell if you use, in this case, the 6 qubits to create 64 degrees of freedom, representing the discretized solution on the 64 cell mesh. So that's a very useful little quantum circuit. Now this can easily be extended to multiple dimensions. So if you then say, if I want a second dimension, so and also y direction, if the other one was x, so you need then, if for a 64 square mesh, you just need 6 additional qubits, and then of course you create the space or the number of degrees of freedom to represent the solution on that 64 by 64 mesh. And then using circuits like the one shown, you see that the left two circuits show the streaming in the first, so the x direction, left and right, and the third and fourth circuits show how the solution is streamed left and right in the y direction. So you see that concept is actually quite nice, because you see that we really use the quantum parallelism approach here, because adding 6 qubits basically in this case created 64 times more degrees of freedom. So in other words, 64 is the number of cells now in y direction. So relative to the first example, of course, we've got 64 times more degrees of freedom. So that's really just a simple example of the quantum parallelism approach to algorithm development. Now, if you then look at the Boltzmann equation I mentioned, so we have a particle distribution function f that is defined in a state space which defines the likelihood or the velocity that a molecule may have, and also for diatomic gases you would have to then encode for the internal degrees of freedom as well. But that means that effectively you have a convection-like equation on the left-hand side where c then of course is the molecular velocity, and of course this is not a constant value, so it covers a whole range of velocities. And that of course means that in reality then in a what we call a discrete velocity method, we discretize c to a large range of possible discrete values, which means that if you then discretize this equation that way, we effectively get a large system of convection equations coming from the left-hand side of that equation. Now the q is really the big problem. So that's the collision term in the Boltzmann equation. That is a nonlinear term. So for now, if we ignore that term, it means that effectively what we can do is say this quantum walk-inspired streaming of the solution for a convection equation, we can use as a building block for a solver for the Boltzmann equation, in which we have removed the collision term. So what we call the collisionless Boltzmann equation. And to do that, of course, then you still need to look at how can we get this CFL as one condition. So in normally, of course, what you would do, if you discretize C in a number of possible speeds, if you use the CFL criterion to limit your time step, the largest value for C, of course, then sets the admissible time step, which means that for the smaller, or the solution associated to the smaller value for C, of course, they don't move by a single mesh width during one time step. And for that reason, then but it's too detailed to go into this now, so you can find this in the papers I wrote in the last few years. You can use what we call the reservoir technique to sort of say, actually, we move all of them by one mesh width if we devise this reservoir technique, where we effectively delay the update for the slower moving parts correspondingly. So just to see what it looks like. So this phase space for a two-dimensional flow is a two-dimensional domain. So U and V are the molecular velocity. So the way to look at it is as follows. So if we have a flow moving left to right here, hitting this object, A is a flow in an undisturbed state. So it has a velocity that is non-zero on average. So you see that the peak of the distribution function is moved from the 0 point, which means that on average, so this gas has a speed moving, in this case, from left to right. Now, if you then move this gas so it streams towards the object, of course, the flow cannot go through the object, so it will have to flow around it. And what this means is that particles will start colliding with the gray object, and they will start bouncing back. So the second spike in the distribution function shown in B are basically the result of particles being reflected back from that solid body. And in doing so, you can then actually account for the presence of this body. And that effectively then allows us, using this streaming operator, to solve the collisionless Boltzmann equation as a set of a large set of linear convection equations. But of course, the boundary condition actually, and I don't have the time for this today, so you can find it in the papers I've written, is of course another crucial thing to consider. But clearly, this was, for us at least, it was a big step, because we, in theory, in this simulation method, and we could let the quantum algorithm run, and while it's performing subsequent time steps, there is no need to transfer or convert to the classical domain. So we don't have this measurement and reinitialization cost every single time step that we take. Of course, at the end, of course, you would still need to measure. So to get a really detailed flow field data, of course, we still have this issue of needing many repeats or many concurrent realizations taking place. Okay, so that's what I wanted to say about kinetic modeling and potential. So just to summarize, because I think we're heading towards I think 1.5 hours here. Clearly, both approaches that I mentioned, I see have potential, but both of them clearly also have got a number of remaining limitations, and those are things that I need to work on, and I am working on. So the hybrid classical quantum discoupled approach is definitely still something to consider. And also recently there is a lot of work in the quantum computing literature on quantum variational methods. So in some ways, or in many ways, these things also are a manifestation of a hybrid quantum classical approach. So clearly this approach has potential, along with challenges that need to be looked at. Now, for the second branch of work I mentioned, so the algorithms that are designed to more or less completely be performed on a single quantum circuit, so without intermediate sort of transfers or conversions to classical data. Of course, there are many challenges involved as well. So how do you represent linear terms? How do you impose boundary conditions? And also, of course, if you look at a typical CFD algorithm, of course, what you often find is that a small number of steps or a small number of components of this algorithm take up most of the CPU time. And that, of course, then justifies doing something like this hybrid approach with an accelerator-like approach. But of course, it still means that all the other tasks that a CFD algorithm performs still need to be conducted as well. So one of the things to really look at is that even if you can devise then the quantum algorithm to tackle efficiently a compute-intensive part of the algorithm, it's still then the question of, would you still then need to execute the bits that are the parts of the algorithm that are not suitable for a quantum implementation? Would you still then execute those on a classical computer? So clearly there is a range of issues. So in my book, in my view, of course, coming to this conclusion, there is potential. I'm happy to say, and also, of course, otherwise I wouldn't be presenting today, and also I wouldn't be spending my time investigating this at the moment. But clearly, I'm also realistic enough that there is a whole range of problems that need to be considered. So just to remind you, the initialization of the quantum state is a major issue. The measurement problem, so obtaining output, is a major issue. Representing nonlinear terms is an issue. And of course, the fact that in the quantum circuit model, at least, apart from measurement, all the other operators have to be unitary. So there is a whole range of limitations that you're dealing with. But it is an exciting line of work. I'm really enjoying it. So I hope to find in the future some more funding and some PhD students and postdocs to work on it. At the moment, it's a relatively small activity in Glasgow. So we hope that we have the options of growing this a bit further in the coming years. But overall, I think the quantum computing has really grown a lot. So the community of people involved in quantum computing research is actually quite large. But people looking at the kind of computational engineering applications that sort of which CFD is one, of course, is still a relatively small group. So that's why I was quite intrigued to hear about your activity this week. So I'll leave it here. I hope you found this presentation useful, and I'll happily open the floor for questions.
Hello, sir.
Hello.
Yes, sir. This is Rashekar here. Sir, I have some basic question. Now you are talking at the level of CFD implementations in quantum environment. So I would like to know the computations can be simulated for any concept in quantum simulators.
Well, the thing, most quantum simulators, of course, they take the view of the quantum circuit model. So if you can create a part of a quantum algorithm and you can specify that as a set of gate operations in a quantum circuit model, of course, then there is a whole range of successful quantum computing simulators. Of course, then so what specifically what aspect are you considering here?
My question is now I am basically from computer science. I am new to this field. Now I am working on machine learning with computer science. So can we realize the results in simulators, quantum simulators? Can we get the results?
Well, you can. So in developing the algorithms I showed you, of course, I used quantum computing simulators. Now, of course, one of the main things to consider is that the quantum simulator, of course, is a classical simulation. So what you see is that the resources that a quantum simulator takes, if you take the full, what we call the full state vector representation, of course, means that the computational resources of the quantum simulator, of course, scale exponentially with the number of qubits. So that means, for example, that if you now look at what you can actually simulate with the quantum computer simulator, for the machines that I have available to me in the lab, going beyond 30 or 32 qubits is actually a big problem, because the time and the memory involved is significant. So for supercomputers like you find in big research labs or the national facilities, of course, people are now able to run simulators with up to sort of 45 or 47 qubits. But so to come back to your question, yes, so a quantum computer simulator will simulate what the algorithm does in terms of either an idealized form, or you can even account for noise. But of course, it has this limit that the problem size is limited. So for the future, of course, this is a problem. So if you want to look at classical, if you want to look at computing algorithms that involve more than for example 30 or 40 qubits, the simulation of that algorithm on a classical computer-based quantum computer simulator, of course, is a challenge. So that's really where I'm at the moment. I'm working with a team of computer scientists at Glasgow to sort of find ways of optimizing this this aspect of my work as well, because clearly it is a bottleneck in testing and analyzing quantum algorithms. Once you go beyond, mainly if you go beyond about 30 qubits, you see that most Linux workstations are really hard pressed, of course. So especially if you go to 40, of course, the challenge becomes very significant. So yes, so in Glasgow, I'm working with a team of computing scientists, and we're looking into ways of speeding up and improving that process as well. So I hope that answers your question.
Yes, sir. Thank you, sir. Thank you so much, sir.
Any more participants having questions?
Sir, I have some two basic question actually. Very
okay.
very basic question.
Mm-hmm.
So this quantum state is represented using a vector.
Yes. If you use the
Why
if
it
you
is
use,
so like?
well, this is the this is one way. Of course, quantum mechanics, of course, comes in different formulations. So if you take the if you use the approach where we use a quantum if we use so you could, of course, also, for example, use like the Heisenberg formulation. But if you use the traditional wave function based formulation, of course, then you would then associate that wave function with complex amplitude. So it's a good question. So there are alternative ways, of course, of describing and getting the governing equations for quantum mechanics. But for most work I've seen in quantum computing and quantum computer simulators, this definition of the quantum state vector using a set of complex amplitudes is the sort of most generic and most often used approach. But you're right. So you could ask yourself why you do that, because there are alternatives to this formulation. You're right.
Yes, sir. Thank you, sir. Thank you.
Okay, any further questions?
Other participants, are you having any question? You can please ask. Sir, I am Dr. Mukul Shastha from Vardhaman College.
Okay.
I have a question. During my PhD time, I had made a code in C, and
Yes.
it used to take too much of time by simulation. It was FSI, fluid structure interaction.
Yes.
So at that time, I heard a lot about CUDA GPU.
Yeah.
And they are doing live simulations with that. So if I compare the CUDA coding or the CFD simulation in CUDA as compared to these simulations, how can we, to what extent can we compare, or will it be logical first of all to compare or not?
I think it's a good question. So as a team in Glasgow, we're always looking at hardware development. So the arrival of useful graphical processors and then the arrival of CUDA, of course, also led us to have a look at this. And we have written papers in the past where things like GPUs and FPGAs were investigated. So clearly, one way to look at the work I presented today is that the quantum move to a quantum hardware is in some ways in line with what you mentioned in terms of the availability and the availability also then of languages like CUDA. So you can see it as a way of improving relative to a general purpose CPU. So in that sense, it is fair to say that if quantum hardware would be becoming more widely available to us, of course, you would actually but then need to answer the question of, well, in CFD, starting from CPUs, is the improvement offered by GPUs and CUDA and things like FPGAs, for example, isn't that more promising than a switch to quantum hardware? And that's actually a very important question, because ultimately, of course, if you're a CFD user, you don't normally care too much about what the actual underlying hardware is. You just want your simulation to work reliably and quick. So it's a very good question. So I think ultimately, of course, if people can really prove an exponential speed up for CFD algorithms on quantum computers, ultimately, of course, then you can expect that quantum computers will outperform then things like GPUs and FPGAs, but we're not there yet. So I think definitely it's a fair point that if you regard quantum hardware as a coprocessor that is slowly but surely arriving in the coming years, then it is fair to say that, of course, we should then look at its potential relative to what things like GPUs or FPGAs would offer us. And I think no one knows the answer yet. So I'm in no position to answer it yet. But it's a very, very fair question and a very relevant one, because we shouldn't get dogmatic about that. We should really, in any case, go down the quantum computing route, because it may not be the case that ultimately this is what is the most promising route. But I think the answer is still out there. So I think all routes are worth investigating. So I completely see, and also in our lab we have done quite a significant amount of work on improving CFD solver performance on GPUs and the Intel Phi sort of kind of processors. So definitely there is scope to investigate all of these different things, and who ultimately is going to be the winner, I think it's very early to say at the moment. So I can see where you're coming with this question, because it's an important thing to consider.
Yes, sir. Thank you, sir. Other participants, if you do have any question, kindly unmute your mic and you can ask the questions. I assume there are no questions. So I would like to request Dr. Deepak for the vote of thanks. Deepak, sir?
Yeah. Am I visible and audible? Mukul, sir, am I audible to you?
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yes, sir.
Yeah. So respected and distinguished speaker of the event, Dr. René Stegel from University of Glasgow, Aerospace Engineering, and our head of the department, Dr. P.S. Rao, our convener of the program, Dr. H. Venkateshwar Reddy, and another convener and head of the computer engineering department, Dr. A. Rajnikant, our faculty members of the department, all the invited guests and delegates. It's my privilege to have been asked to propose a vote of thanks on this great occasion. So I am Professor K. Deepak, Mechanical Engineering Department. I am in thermal engineering with specialization in thermal engineering. So it's a great honor for me to propose a vote of thanks, and I'm very excited to see the great speaker here. So thank you very much, sir, for being with us, for taking your valuable time out of your busy schedule, and you have explained it very clearly and precisely about the quantum computing algorithm for the practical engineering applications on CFD. So thank you very much, sir. And I thank our head of the department for getting the idea of making a program like FDP on this quantum computing. It's very much beneficial for all the faculty members as well as the research scholars. And it's very great, and you are very kind that you have proposed some of the scholars who are interested to do the work at your University of Glasgow. Thank you very much, sir, for that proposal. And
yeah, well, definitely. Of course, in the UK, of course, we are academics, so we are trying to build links with teams in the UK, but also, of course, abroad. So if I would be very interested in seeing what in your institute the research interest is in this area, and of course, if there is a way of collaborating or exchanging information, or even sort of once the Corona thing is over, sort of visits or seminars, of course, we would definitely be interested. Yes.
So at the outset, I would like to thank our principal, Dr. JVR Ravindra sir, for always encouraging us to conduct such programs in the department. Thank you very much, sir. So I would like to thank our head of the department once again for his idea of making this program in the quantum computing. So I would like to thank all the department faculty members for their encouragement and their effort and support, and making this arrangement of conducting the event, coordinating with all the delegates and invited guests and participants in making this event a successful one. So I congratulate all the participants and delegates here who are with us, making this program a grand success. Thank you all. Thank you very much, sir.
Thanks for the invitation, and it was a pleasure talking to you.
Thank you, Professor. Thank you very much.
Mukul sir, you have any further announcements?
No, sir. Thank you all for being there. And for tomorrow's session, we'll share the link for tomorrow's session. Thank you, sir, for taking out some of the valuable time. Thanks
Okay,
a lot.
well, you're welcome. Thank you.
I think we can wrap up this meeting.
Okay.
Okay, thanks
Bye.
a lot, sir.
Bye now. Sir. Good evening.
Bye, sir. Bye, sir. Good evening. Take care, sir. Take care.
Thank you.